our home countries, I guess. So Naoki's going to talk about screenings in applications. And start whenever you want.
Okay, thank you for inviting me to give a talk here. So today I talk about a very introductional talk about screening operators and some applications. First, I talk about motivation of screening, but usually I talk about lots of examples of screening operators. Because I'm not sure how many people study screening operators because it is a little bit different things to study versus algebra. So I want to talk about a lot of introduction or some elementary things of screening operators, and later I talk about application of a lot of representation theory of vertex algebra. So first I talk motivations. So why screening operators? So screening operators used to characterize some prefiguration of vertex algebra. You know, one of the famous examples is the Virasoro ones. So you consider alpha z. This is a Heisenberg field at the level now 2k plus 2, a little bit different. And now, in this case, you consider the Virasoro vertex algebra of central charge ck. This is minus, I missed 6 root k plus 2 minus 1 over root k plus 2 squared. And now this is, we know that such a Virasoro vertex algebra is embedded in Heisenberg vertex algebra. And also, the image of Virasoro vertex algebra can be characterized by the kernel of screening operator, this kernel, integral E alpha z, if k is generic. And also, k is special value, this kernel is a little bit bigger than Virasoro vertex algebra. For example, k plus 2 equal 1 over p, it becomes some triplet W-algebra. Okay. But now we consider generic case. And Virasoro vertex algebra is known to be only determined by the central charge. And ck and now does not change if you change square root of k plus 2 to minus 1 over square root k plus 2. So we know that the kernel, if k generic kernel of E alpha z, is isomorphic kernel of minus alpha over k plus 2z. This is known to be a duality of Virasoro vertex algebra screening operator. So now we consider prefiguration of principal W-algebra or simply algebra G. For generic K, it also can be described by a kernel with intersection of kernel of screening operator. It forms like E minus alpha I K plus H check Z. This alpha I is just a Heisenberg field corresponding to root system of G, and H check dual constant number. And then the duality of Virasoro screening operator implies that the Feynman-Franke duality, because each kernel of a screening operator becomes different screening operator. Now I denote by E alpha I check Z, but now we can identify with such an intersection of kernel is isomorphic to also different principal W algebra corresponding to Lagrange dual of G. And now level L is related by the R check K plus H check times L plus L H check equal 1. This is a famous Feynman-Franke duality. So this is one of the reasons why we want to understand the screening operator, because some screeningization gives interesting proof that such a duality. So another reason why screening operator is so important is that screening operator is a useful tool to study concept isomorphism. Now we take G, we put some notation. G as simply algebra, BKG is a fine one. LKG is a simple quotient. Now, due to Wakimoto for SL2 case and the Feynman-Franke for general G, VKG has prefiguration of, in fact, the VKG is embedded in the beta gamma system. Since the product of beta gamma system, the number is just a dimension of n plus, the tensor Heisenberg vertex algebra. And plus is the upper nilpotent subalgebra, and the Heisenberg part is called Heisenberg vertex algebra associated to Cartan subalgebra of G. But now level is K plus H check. This is called Wakimoto representation. And also this image can be checked by the intersection of kernel of some screening operators of K generic. So now we consider G is ADE type and K generic. Now we're chasing this embedding. We first consider diagonal coset of affine vertex algebra embedded in VK minus G tensor L1G. And it is a little bit need to some analyzation, but we know that it's isomorphic to kernel coset of Heisenberg coset of semi-infinite cohomology of loop subalgebra Ln plus 2 for VK minus G tensor L1G. But now we use Wakimoto realization of VK minus 1G. We get this coset embedded in the Heisenberg coset of a semi-cohomology of beta gamma system tensor Heisenberg tensor L1G. But we can compute this complicated coset. It's just isomorphic to Heisenberg algebra, but the level is a little bit different. And we know that using the screening operator of affine vertex algebra, this image of coset inside Heisenberg vertex algebra can be also characterized as kernel of screening operator. And we know that such a kernel screening operator is just an exponential of minus alpha I over L plus H check V. So we can identify with this coset is isomorphic to W-algebra. This is proved by famous Arakawa-Kuroti-Grinshaw coset, and a very useful and very great result for the coset theory. So, and also, this motivated from this cost construction, we consider module side. Now we consider module of VKG, written by VK minus 1 mu tensor L1 u. This decomposed to diagonal coset of VK lambda, and T L mu lambda is coefficient. But now we know that it is a module of W algebra. And using a little bit different but similar technique, we know that this coefficient module can be identified with kernel of some screening operator. A little bit complicated, but also we know that such a screening operator. And this description is used to identify with coefficient module is isomorphic to some Greenfield so-called reduction of bound module. So this means that, first of all, if you know that if you want to prove some coset isomorphism, you can use screening realization. And also, screening realization gives some nice motivation to analyze a coefficient module appearing as a decomposition. And possibly is used to identify with a different construction module. So today this is some motivation, and I want to generalize such a technique to other cases, and using to prove some duality, coset, and also recently, and lots of triarity has been proved, but I want to prove such a triarity using such a screening realization. Okay, this is motivation. This is motivation. So let's try first start from examples. So first example, this is beta gamma system. Beta gamma system is generated by beta z and gamma z related by this OP. And if you consider lattice L, this du plus dv, and you in the product of uu as equal to 1 and pp equal to -1 and up equal 0, and you can define lattice vertex algebra associated with L. In fact, this is vertex subalgebra. And now we consider VU plus V, this is vertex subalgebra, OP lambda, VL, generated by Heisenberg element U and V, and the lattice part EU plus V and E minus U minus V. So we consider, and then we get the embedding of beta gamma system inside this vertex subalgebra defined by beta goes to EU plus V, and gamma goes to minus U, E minus U minus V. You can check this as just a vertex homomorphism, and easy to see that this is injective. And also, non-trivial part is this image coincides with the kernel screening operator. And beta gamma system, this image can be identified with kernel of a Ross equation, an integral of EUZ dz. This integral means that formal residue, this is just a coefficient of z minus 1. So this kernel means that there's a kernel of EU0. So you can compute this image as inside the kernel of this EU0. So because EU is just an element of lattice vertex algebra, so easy to check this statement. This is a first simple, very simple example. But this is starting point. So now we consider Virasoro case. This is second example. So Virasoro vertex algebra is generated by LZ of central chart C satisfying this OP relation. And now we take K and take CK as same as the first slide. Now we consider pi, the Heisenberg algebra generated by this alpha Z. Then the Virasoro vertex algebra of central chart CK is embedded in pi by the middle equation, LZ maps to 1 over 4k plus 2 times square alpha Z plus 2k plus 1 derivation alpha. And also you can know that this image coincides with kernel screening operator if k is generic. If k generic case, this image is in the kernel of E minus alpha over k plus 2z. So that possibly this statement is a little bit difficult because this exponential is not the element of lattice vertex algebra because k is arbitrary little bit. This cannot be identified with some element of lattice. So how to check this statement? Usually I use a mathematical package OPEdets. So today I will explain how to check this statement. This is a very simple case, but it's a very this is some introduction talk, so maybe it's good for some students or some people. So we have some OP relation. First, alpha Z, alpha W is just a Heisenberg one. And also formally, if you consider alpha Z and the exponential minus alpha over k plus 2 W, as the singularity happens only Z minus 1 over Z minus W, and the coefficient is just a minus 2 exponential minus alpha over k plus 2 W. This minus 2 coming from the inner product of alpha and minus alpha over k plus 2, because alpha is 2k plus 2, so it becomes minus 2. And also we have derivation formula. A derivation of exponential becomes also some power comes down our coefficient, but now we need to normally ordering. So it becomes the minus 1 over k plus 2 times alpha Z times exponential 1. So we want to know that the kernel of this exponential, but we only need the coefficient of 1 over Z minus W in the OPE of exponential E minus alpha k plus 2Z in some linear equation. This is just the only candidate happen in conformal weight 2. In conformal weight 2 space in the Heisenberg vertex algebra has only square alpha square and derivation alpha. So we put the formal coefficient S and T and consider the linear term, and we want to solve can we find some solution of this kernel of screening operator. So real package following. So we first take OPEdets and define A and E. Now E is not field, but to compute the kernel of screening operator, it's no problem if you define E as some field. And now we define OP and A and E as a standard way. And the first statement says this first OPAA means that defining OPE of AZ and AW. And second one is define OPE of AZ and EW. But we cannot define OPEE, but we don't need to use it, so we can omit it. And also we define E prime, this is derivation. E prime is just a normally order of minus A over k plus 2 and E. And now, and the second, 7 and the 8th line, I compute the residue, OPE of coefficient of 1 over Z minus W. OP pole 1 means that coefficient 1 over Z minus W. OPE of E and linear term as A squared plus T derivation A. And you get only linear term, only one term, but coefficient is 2s plus 2ks minus T. Now we solve this solution, 2s plus 2ks minus T equals 0, for example T. We get T as now 2s plus ks. And we substitute this T to twice of s plus ks, and we get the answer. Answer is just one dimensional. It's just s times a squared plus 1 plus ks derivation A. If you take S equal 1 over 4k plus 2, you get a Virasoro field, and this Heisenberg algebra corresponding to the image of a generator of Virasoro field. So the central charge is CK, just CK. Okay, this is how to check this statement, and very easy if you can use this OPEdets package. So now we go to third example, and this is just a affine SL2. Affine universal affine Virasoro algebra associated SL2 at level K is generated by H, E, and F, and satisfying the standard OP relation. And Wakimoto proved that this is embedded in the beta gamma system tensor Heisenberg. The map is E goes to beta, H goes to minus 2 gamma beta plus alpha, and F goes to minus gamma square beta plus K derivation gamma plus gamma alpha. And also if K generic, if we can check this image coincide with kernel screening operator. Screening operator is written in the last equation. It looks like kernel of beta z and exponential minus alpha over k plus 2 z dz. So you can check also, you can check this statement by using OP package in the same way. You also need to add you need to add bosonic beta and gamma and define this screening as a normal order of beta and E, and you can check kernel. You can check this image in the kernel of the screening operator. Okay, this is now we talk about 3 examples. One is beta gamma system, second one is Virasoro, third one is SL2. These are very easy, and you can check everything very explicitly. But now is there any question? If not, I go to the affine case. So affine case, if you want to get screening operator for arbitrary affine VKG, you need a little bit complicated computation. But today I want to explain this secret. So now we want to generalize for affine SL2 case to arbitrary affine VKG case. Now we put B minus. B minus is the opposite polar subalgebra, and we consider the differentiation of the left action G on flag polarity G over B minus, and this induces Lie algebra homomorphism, Lie algebra G to differential ring, D and also differential ring over flag polarity G over B minus. And we consider the restriction, the large n plus. This is in fact the open dense of this flag polarity, and this is the Lie algebra homomorphism G to differential ring on coordinate ring of n plus. So now fix an affine isomorphism. Now n plus is unipotent subgroup, so this is a affine space, so we can identify with the Lie algebra homomorphism and by using exponential map. And now we want to compute this differential representation, but there is known to be a very famous formula. I want to call Frenkel formula. This action can be computed as a dot x can be computed by minus x and bracket plus and x inverse ax. And this plus, bracket plus means that projection G to n plus. And this product, right hand side, the product is a matrix, matrix multiplication. So, and now, and if you get such a differential representation, we consider affinization of the representation gives some Wakimoto representation as desired. But this is formal recipe. You don't need to understand this statement because now I give example. Now you forget everything. So we consider SL3 case. Now we fix n plus to large n plus. So SL3 case, and n plus is just an upper important part with ID node x1, x2, x3. And it maps to large x. It's just by using exponential. E minus x1, E minus x3, and E minus x2. It becomes the diagonal part just 1, but the upper part is a little complicated. Now we compute this differential representation by using Frenkel formula. Because now, first one is just E12 times x. You're computing using the Frenkel formula. Frankel formula is just this one, minus large x inverse ax plus. I put I put this matrix and large x inside this, computing multiplication and taking projection and so on. We get this result and so on for element of Lie algebra G, SL3. So result is, now you understand that E1 is just a derivation x1 and E2 is derivation x2 and so on. Why? Let's check. E1 is derivation x1. So E1, this is E1. E1 is just E12. E12 acts on x, it becomes just this one. You see, if you consider derivation x1 acts on large x, becomes diagonal part should be 0 because that's a scalar, so it should be 0. And 1, 2 component, this now large x is minus x1, so if it acts on derivation x1, it becomes minus 1. And 1, 3, it should be becomes x2. And minus x2 becomes 0, right? So this result says that E12 acts on x as a differential of x1. In the same way, you can compute this expression from this formula. And now we replace this derivation xi and coordinate x large xi by differential xi. We replace differential xi to beta I and coordinate xi to gamma I, and with some additional term. In fact, following. Now we omit the normally order product, and E1 becomes derivation x1, so it becomes just a beta 1. E2 is just a beta 2 plus gamma 1, beta 3, and so on. And the black right hand side on the I wrote black one is coming from the differential representation part. But now we add the red one. The Heisenberg part, we need to add the Heisenberg element alpha 1 and alpha 2. And lower nilpotent part, I need to add first for F1, I need to add gamma 1 and alpha 1, and some coefficient plus derivation of gamma 1. F2, we need to add gamma 2 and alpha 2, and some coefficient and derivation gamma 2. In the same way. And this defined embedding affine SL2 to beta gamma tensor 3 tensor Heisenberg by this algebra. This is a recipe to construct such an embedding. You only need to decide this coefficient, but the other part is the same as I explained for any Lie algebra G. So now we want to know the screening operator of this embedding. And to construct the screening operator, we need to compute the right action of n plus to n plus. And first we consider left action on flag variety, but now we consider right action of n plus to n plus. This is that the Lie algebra homomorphism n plus to differential ring of n plus. And this also can be computed by the very simple form because now A is n plus, so it's very easy. And the SL3 case, we consider E12 act on X by this one, and E23, it becomes this one. So this implies that E1 is just has this differential representation, E2 becomes this one. And then the generic case, our original homomorphism, find SL3 embedded in beta gamma tensor 3 times Heisenberg is kernel. If K generic, it coincides with kernel of one is this screening operator, and the other is this screening operator. And you see that the exponential is the first one, this alpha 1, and the second one, alpha 2. But coefficient part coming from right action for E1 and E2. You see beta 1 plus gamma 2 beta 3 comes from the affinization of the differential representation of E1. And the beta 2 coming from this derivation x2. In the same way, you can compute the screening operator by using this right action. This is the rule to get the kernel screening operator. And this is the rule to construct the screening operator of affine vector algebra. This is natural generalization of SL2 case. Because if you compute SL2 case, we get just a beta z and exponential. So this is the same as I explained at the third example. But you know that this expression really depends on the choice of affine isomorphism n plus to large n plus. In fact, if you use another affine isomorphism, small n plus to large n plus, defined by one exponential, the power of exponential is just everything. minus x1, minus x2, minus 3. It becomes a little bit different. You can find this 1/2 coefficient happens. We can also compute everything by using same rule. And you get also obtain a different embedding. This image can be also captured by the kernel screening operator. But using this coordinate, you get a different screening operator. It becomes a very symmetric one because our coordinate is very symmetric, so the screening looks like very symmetric. And if you know that the explicit formula of this embedding, I wrote here that, for example, you can see E1, E2 looks like a very symmetric one, but F1, F2 is very complicated. A little bit looks very symmetric because I choose symmetric coordinate. You don't need to understand this one, but so this means that the screening operator of a affine vertical algebra is not unique. It really depends on the choice of a coordinate system. So you can choose, if you fix one affine isomorphism, re-algebra n plus to regroup n plus, you get free-visualization of affine vertical algebra and get the screening operator of affine vertical algebra. Okay, so now we consider super case. Super case is still conjecture. It's in progress, joint work with Shigenori Nakatsuka. We consider G as a basic classical Lie algebra. This means that G has some SLMN or OSP M2N and some exceptional case F4 G3 and D21 alpha. And now we consider supergroup action on superfractality. And this using a super geometry, we get the Lie superalgebra homomorphism G to differential ring of n plus. I mean, I should say differential super ring because we need this includes auto derivation. But now we can find such a similar Frenkel formula similar to Frenkel's one. A dot x can be computed in this way, but we need to find some parity here. And this matrix multiplication is defined by this formula Aij, Bij. I mean, the right-hand side is defined by matrix multiplication, but this matrix multiplication defined in this way. So you see that the usual matrix multiplication is Aij, Bij is just Aik times Bkj, but now a little bit different. The order is different because x possibly contains odd coordinate, so this multiplication a little bit sometimes different from Aik Bkj. So we need to add possibly happen some parity. But if you define multiplication rule in this way, you get this formula to compute differential representation, and you consider affinization of this morphism. You get the free-visualization of affine vertical superalgebra to embed in the beta gamma system tensoring dimension of even part of n plus times BC system tensor dimension of odd part of n plus and the Heisenberg. And also you can compute this image. You can compute the kernel screening operator by using the same way. Maybe it's a little bit joint work. So, for example, a little bit in progress. So, for example, if you compute the OSP12 case, we can compute this image as in this one, in this way. E alpha and F alpha is an auto element, and E2 alpha, F2 alpha, and H is the standard S2. And E alpha and alpha is a unique auto simple root, but non-isotropy. And this image can be characterized by using screening operator and the last equation. It looks like P plus C beta T and exponential minus alpha K plus 3/2. 3/2 is the Dirac number of OSP12. And in general case, we expect we can compute in the same way to get the free-visualization of affine superparticle algebra and also get the screening operator of them. Okay. So now we go to screening operator of W-algebra. So our idea is first we compute screening operator of affine vertex algebra, and now take Dirichlet circle reduction and get the screening operator of W algebra. This is my idea. So W algebra is defined by these three data. One is G is simply algebra. Now we assume the simply algebra, but later I can also assume that G is simply superalgebra. And F is nilpotent element in G, and X is semi-simple element in G, satisfying that adjoint X defines a half G grading on G, satisfying good condition for F. And then W algebra is defined by Dirichlet circle reduction of VKG associated to F. And really it's defined by the Delos cohomology of VKG tensor phi tensor F for some D. And phi, large phi is a neutral fermion vertex algebra, and real algebra case is just some beta gamma system. And F is charged fermion. This is just a vertex algebra. And D is defined by the last line. E alpha Z comes from a phi one. This bar phi and bar phi star is a field of charged fermion. And this large phi alpha, and the last line you can find large phi alpha Z. This is coming from neutral fermion one. It's just some beta gamma system element. Anyway, this is definition. So now we prepare some notation. Now some upper nilpotent subalgebra n plus it becomes G positive plus G0 plus. But G0 plus is just intersection of n plus and G0. It means that n plus contains all G positive part and some part of G0. And then, the large n plus, n plus can be decomposed to G positive part and G0 plus, large G0 plus. Now, G positive and G0 plus is both real algebra, Lie groups are unipotent. We can choose a affine isomorphism, denoted by X positive and X0 plus. And define affine coordinate just X on n plus by X positive times X0 plus. The point is that I fix the order of this multiplication. I think there is some choice on X positive and X0 plus, but I fix the order X positive on left I put the X positive on left and the X0 plus on right. And using this X, we have embedding affine vertex algebra embedded in beta gamma system, tensor Heisenberg in the same recipe I explained. And also get screening operator. And now we take Dirichlet circle reduction. This implies that W algebra embedded in beta gamma system tensor dimension, but the number of tensoring is just the dimension G0 plus and tensor Heisenberg. Maybe let's go, we want to say that this is one key mode representation of W algebra. And also, this construction gives the screening operator of W algebra. If VKG is kernel of screening operator, and PIV is coefficient part at the field of beta gamma system, and then W algebra, the image of this embedding of W algebra is also coincide with kernel screening operator. It looks like some PIV tilde times an exponential, and the PIG tilde deduced from PIV by the following rule. If alpha I has degree 0, this means that root vector of E alpha, root vector has grading 0. I mean, if alpha I has grading 0, means that root vector E alpha I has grading 0. I mean, it's an element of G0. Anyway, we define the degree of simple root in this way. And now, alpha I is delta 0, PIG tilde is just a PIV. And alpha I has grading 1 over 2. We just any beta JZ in this PIV maps to this phi alpha. This is field of neutral fermion. And this alpha corresponding to xj. And alpha I has degree 1, beta j equals to some scalar. And any simple root has grading 0, 1, or 1, this half and 1. So this is all rule. And this is a result of my advanced paper and some statement. And this statement proved by appendix by Shigenori and Katsuka. And for example, you forget such a rule. I explain only rule, example. So SO2 case, you remember that the screening operator, but now you take a principal during Virasoro reduction. This induces the W-algebra of SO2. It's just a Virasoro algebra. This rule is beta z equals to 1. So we get Virasoro screening. And also we consider affine SO2. I computed, last slide, I computed the screening of affine SO3, for example, in this way. This is a subregular W-algebra SO3. Subregular case, this E1 and E3 has grading 0, and E2 has grading E1 and E3 grading 1, and E2 has grading 0. So B2 part is grading 0, so it's same. But this part is a little bit different. If you choose F subregular element is just F1, this beta 1 becomes just 1, but beta 3 becomes just 0. So this becomes just a scalar 1, so it looks like just a Virasoro screening. Other part is just a SO2 screening. That's the result. If you want to choose subregular nilpotent element as F3, if you want to choose subregular nilpotent element F3, I think beta 3 becomes 1, and beta 1 is becomes 0. So this coefficient becomes gamma 2z. It is also another description of the subregular algebra. But anyway, this is one of the ways of how to compute screening operator of W algebra. And the same rule also true. I believe that this is also true for super cases. For example, OSP1-2 case, we have such a screening iteration, and also we consider principal during Virasoro reduction, and then BZ becomes phi z, and beta z becomes 0. So we get the screening operator. This is coincide with n equal 1 superhomomorph algebra screening. So this is another description. Okay, now it goes to application. This is my last part. So we talked about screening operator of beta gamma system and the Virasoro algebra screening, and also screening operator of affine SO2, and also consider screening operator of affine algebra VKG, and which consider during Virasoro reduction, we get the screening operator of W algebra. So you remember that the beta gamma system has this screening realization. And now this observation says that the affine SO2 is first. We have first line says this is standard screening, that this affine algebra embedded in beta gamma system tensor Heisenberg. Now we replace beta gamma system to this screening realization. We need to add this kernel screening beta gamma system. But now in this case, beta z becomes this EU plus b. So this screening of SO2 becomes EU plus b minus alpha over k plus 2. Okay. And also we record that boson fermion correspondence. BC is isomorphic to lattice plus algebra BC. If B is E phi and C goes to E minus phi. I use this result to the next slide. So first of all, we can compute subregular screening of subregular W algebra, or in this way. We have lots of Virasoro screening and one of SO2 screening. And now we use the same trick to SO2 to decompose to beta gamma becomes to one screening, and V beta becomes U plus B. I explained it for SO2 case, but now becomes this one. And also, in the last equation, we use this duality of Virasoro screening. This first Virasoro screening becomes just alpha I. This U plus B minus alpha n minus 1, k plus 2, k plus n becomes this minus k plus n, U plus B plus alpha n minus 1. But the last one I didn't change anything. But anyway, we get this realization. And next, we consider principal W superalgebra of SLN1. We can compute the SLN1 screening as screening of Virasoro 1 and BZ and E minus alpha n over L plus n. But this alpha I and alpha n has a root system corresponding to SLN1. And so this BZ has using the boson-Fermi correspondence, this becomes E phi. And if you assume that this relation k plus n times L plus n minus 1 equal 1, using this Heisenberg isomorphism. Left-hand side is a Heisenberg field defining screening of subregular W-algebra. And the right-hand side is just a Heisenberg field defining screening operator or principal W superalgebra. And we say that this is isomorphism between Heisenberg algebra. This means that we can identify two screening. So the theorem says that if you, but a little bit domain of this kernel is or domain of screening is a little bit different. So we need to take Heisenberg commutant or adding something. We get isomorphism using these screening operators. So this is a result by Thomas and me and Shigenori. And moreover, if you assume that the existence of screening operator of affine basis algebra of SLN1, you can get also this affine basis superalgebra embedded in some beta gamma tensor some BC system tensor Heisenberg. And now we take Pi to E phi I and Ci to E minus phi I. We can compute commutant of even part affine GLN inside the super affine SLN1. And using same technique by Arakawa critical initial coset, you can get this coset can be identified with kernel screening operator in this way. And also assume that the last equation, last relation, we get Heisenberg isomorphism defining screening. And this induces famous critical initial triarity. This is one of example that of the first equation proved by us, and also we assume that screening operator of affine super screening, we also can prove that the triarity. The relation here. Moreover, if you consider module cases, this is affine SLN1 module, and this decomposed to affine GLN module and some coefficient. And we can easy to conjecture that this coefficient module can be identified with kernel screening operator using screening operator of subregular W algebra 1. But this is still conjecture. But we can expect such a statement. And I guess that's possible to maybe useful. Now we can using same technique, and if you assume that screening operator of affine OSP 1 to n, we can also prove that this coset isomorphism. This first one is Feigin-Frenkel duality, and the last one is a coset of SP to n inside OSP 1 to n, using this relation. And maybe this is also proved by Linshaw and Shashank, Andy and Shashank, and I think if we can prove this statement using screening operator, we can also possibly prove that the representation part, representation of affine OSP 1 to n can be decomposed to affine SP1 and coefficient module. And also coefficient module can be identified with some kernel screening operator and can be identified with a difference of construction by using from the bar module of FP. So anyway, we have lots of application on this statement. This is a list of we can do. First one is type B coset of ACL. Critical initial coset only consider ADE type, but I guess this is some B type statement. And this is joint work with Thomas. And also, if you consider some screeningization of GLN W algebra, and if you forget one screening, you get the natural affinization of coproduct of finite W algebra. Finite W algebra case is known constructed by Blanda and Kleshek, but I guess this is some affinization. If you take the algebra, this induces Blanda and Kleshek coproduct W algebra, finite W algebra. And also, in generalization of this construction, you can get the parabolic induction by using also screening operator. This is a finite W algebra case. This is known constructed by Pleme and Rosset, but we can construct a fine analog of this statement by screening. And also a down-pitch path SL2 case, down-pitch used the fine SL2 embedding in the Virasoro tensor some lattice algebra, but we can explain this embedding by using forgetting one screening. So this means that we can generalize this statement for SL3 case in this way, and so on. So, and this is useful to construct non-admission level representation. So I guess this is also useful to understand more. Moreover, final statement is stepwise reduction. This is W-algebra or Hook type W-algebra has some nilpotent subalgebra and can define dream-field circle reduction. And the statement is the dream-field circle reduction of Hook type W-algebra becomes different Hook type W-algebra. You can prove this statement also only using a screening operator. And moreover, we expect a lot of application of screening operator. And if you are interested in a screening operator, please use and solve a lot of problems. Okay, thank you. I stop here.
Hey, let's